the busiest shipping lane in the world. A narrow scar of water only 22 miles wide yet cold, restless, and unforgiving, separating an island from a continent, separating languages, economies, histories, and for 2 centuries daring engineers to defy it. For more than 200 years, the idea refused to die. As early as 1802, when horses still ruled the roads and oil lamps flickered against the night, visionaries imagined a permanent link beneath the sea. Dreams were drawn on paper long before technology could catch up. In the 1880s, they even tried to make it real, driving exploratory tunnels into the earth, testing the chalk, listening to the water above. But the sea always wins. Every attempt ended the same way, defeated by flooding, politics, fear, or money. 4 times the project collapsed. And then, finally, after generations of failure, the British and French governments made a decision that would change geography itself. 2 nations agreed to take one extraordinary risk. They were not just building a tunnel. They were welding together 2 economies, 2 rail systems, 2 cultures. The design was audacious. Not one tunnel, but 3 two-rail tunnels carrying trains in opposite directions, and between them a central service tunnel, a lifeline for maintenance and emergencies. On the French coast, the quiet village of Sangatte became ground zero, transformed into an industrial launch site. On the English side, excavation began beneath the iconic white cliffs of Dover, symbols of isolation now destined to become a gateway. The greatest enemy was not politics or money, but geology. The entire plan depended on threading a path through a very specific layer of earth, chalk marl, strong enough to hold its shape, dense enough to keep the sea out. Drift a few meters too high and the tunnel would hit porous chalk, inviting catastrophic flooding. Drift too low and sticky clay would grip the machines, stopping them cold. The target was brutally precise. A band of rock only 20 meters thick, lying 75 meters beneath the seabed. Years of seismic surveys and test drilling slowly revealed a route where this fragile balance could be maintained. On the English side, another challenge loomed. How do you build a massive tunnel portal into a sheer cliff face? The answer was violence and patience. They blasted away 250,000 cubic meters of chalk, carving a flat platform out of the cliff itself. A new piece of Britain was created with explosives. Across the water, the French dug something different. A colossal circular shaft 60 meters deep. A concrete-lined pit that allowed tunnel boring machines to be assembled and launched far below ground level. Even before digging forward, the pressure down there was immense. These machines were not purchased from a catalog. They were designed and built specifically for this job. 11 tunnel boring machines in total, each a self-contained subterranean factory, kilometers long when fully assembled. The cutter head alone weighed 600 tons, a rotating steel monster designed to grind relentlessly through solid rock, cutting a perfectly controlled line. As it advanced, a continuous ballet unfolded behind it. Spoil removed, hydraulic arms lifting prefabricated concrete segments into place, sealing the tunnel ring by ring. Those segments were watertight. They were the only thing standing between the workers and millions of tons of seawater. The United Kingdom launched 6 machines, 3 driving inland, 3 pushing out beneath the sea. The French machines were different, sealed-face excavators built to operate under pressure. Because their side of the channel was wetter, the rock looser, more treacherous. It wasn't just pressure holding the water back. It was pressure everywhere. Inside those unventilated tunnels, temperatures could soar to 50 degrees Celsius. Miles from daylight, crews worked in a man-made underworld, a pressure cooker of heat, noise, and risk. The service tunnel always went first. Every single meter was a gamble. Engineers watched obsessively for water seepage, the earliest whisper of disaster. Any leak, no matter how small, had to be grouted immediately. A sudden inrush could flood the tunnel and trap an entire TBM crew with no escape. Above them was not just the sea, but the weight of the schedule, the financial clock ticking louder every day. Staying inside the chalk marl demanded absolute precision. A narrow, invisible corridor 20 meters thick was all they had. A beam of light marked the intended path. The true guide, however, was a gyroscope, an electronic compass so precise it could track every curve, every deviation, deep underground with no external reference. Using this, an operator steered a 1,000-ton machine as delicately as a car on a highway. The scale of the logistics was staggering. More than 7.5 million cubic meters of excavated material had to go somewhere. On the British side, they dumped it into the sea, creating a brand new 90-acre coastal platform. They didn't just dig a tunnel, they reshaped the coastline. When you don't know where to put the dirt, you build land. The main rail tunnels followed, larger in diameter, driven faster, demanded to be smoother and straighter to handle high-speed trains. The rails themselves were specially designed to survive heat, pressure, and vibration deep underground. Kilometer after kilometer disappeared beneath the seabed. After 39 kilometers of blind excavation, the service tunnels on each side were separated by just a few meters of chalk. Two separate worlds drilling toward each other through darkness, trusting nothing but instruments. Any miscalculation, any accumulated error, and they would miss completely. Then came the moment of truth. A small pilot hole was drilled. On December 1, 1990, it broke through. The handshake that followed echoed around the world. The final alignment error was less than half a meter after 39 kilometers, 75 meters below the sea. Precision on the edge of the impossible. The chalk marl held. The gamble paid off. Over the following months, the main rail tunnels met as well, completing the physical link. And then a quiet question: what happens to the machines that made this possible? On the British side, the tunnel boring machines were too large to turn around. Dismantling them underground would have taken months. Time was money, so they made a decision. They sealed them in place. 6 enormous British TBMs, each weighing around 1,000 tons, were entombed forever beneath the English Channel, sacrificed to keep the project moving. The French machines were dismantled and hauled back to the surface, their job done. With the excavation complete, the tunnels had to be transformed from raw cavities into a living system. They needed air, light, power, and above all, safety. Giant ventilation fans were installed to push fresh air through the entire length of the tunnels. A failure in ventilation would mean catastrophe. The system was designed to replace the air every few seconds. High-voltage power cables and signaling systems were laid for 25 kilovolt electric trains. The track was precision-welded, smooth enough for sustained high speed. Trains would travel at up to 160 kilometers per hour under the sea. Touch that power line and there is no second chance. Another invisible problem emerged: air itself. A fast-moving train pushes a solid wall of air ahead of it. Pressure waves had to be managed. Fire was the ultimate nightmare. To confront it, every 375 meters an escape route connected the rail tunnels to the service tunnel. That central tunnel became the lifeline, a protected artery running the entire length. Fire suppression systems lined the walls. Emergency lighting was redundant, powerful, impossible to miss. When the first trains finally ran, the engineering triumph was undeniable. The financial reality was brutal. Costs had exploded from an estimated $4.7 billion to nearly $9.6 billion. Technically, it was a miracle. Economically, it was chaos. At the terminals in Folkestone and Coquelles, massive infrastructure rose. Logistics hubs, holding areas, a city built for cars and trucks. Vehicles would drive onto shuttle trains, 40 minutes later emerging in another country. It was not a ferry, but it felt like a voyage, a high-speed underground crossing. The political dream, delayed for centuries, was finally real, but the cost was human as well. 11 lives were lost during construction, a sobering reminder of the price of ambition. At last, the final formalities were completed. The Channel Tunnel opened for business. The impossible had become routine. Water no longer separated Britain from Europe. Steel and concrete joined them instead. 2 years later came the ultimate test. A fire broke out inside a truck shuttle, fueled by tires and cargo, the worst-case scenario engineers had feared. Systems activated instantly. The service tunnel became a refuge. Every person aboard survived. The design was vindicated. 3 tunnels, not one, had saved lives. With the later completion of High Speed 1, travel time from London to Paris dropped to just over 2 hours. Faster than flying, without security lines, without airport stress. A seamless crossing made possible by a century of planning, failure, and persistence. The physical link is permanent now, an unbreakable bond of steel and chalk beneath a restless sea. It stands as one of the greatest collaborative engineering achievements in human history. They once said the sea was a wall. The Channel Tunnel proved it was only a challenge. Human ingenuity found a way through. And even as trains race through the darkness below, the next impossible project is already taking shape. This is the true connection. Don't miss what comes next. Subscribe, Cyberflare Economics.